Remember the previous lesson when we had the compounding, we had a rate divided by the number times compounded to the n times t power. So we're going to keep the rate here at 1 and keep the time at 1. We're going to use an input of n and see what we would get for the output. So I'm going to start with 10 to the first power, which is 10. So I'm going to type that in the calculator. Parenthesis, 1 plus, parenthesis, 1 divided by 10. And then I'm going to take that to the 10th power. And I get 2.5937. And then I'm going to continue this little experiment. What happens whenever instead of 10, I put 10 squared, which is 100, and then 10 cubed, which is 1,000, and then 10,000, and then 100,000, and then 1,000,000 in place of n. So I'm going to do this same problem, but instead of a 10, I'm going to make this 100. And I'm going to make this 100. I get 2.704. So let's go back and change that to 1,000. So 1,000 there, and then another 0 here. I get 2.7169. Let's try that again. Let's add another 0 here, and add another 0 here. So what we're doing is we're dividing by a larger number each time and taking it to the same power. So I get 2.7181. Let's do it again. Let's add another 0. Go over here, add another 0. And I get 2.7182. What do you notice about these output values? The bigger the n value gets, as n approaches infinity, so as the number of times we compound approaches infinity, then this number starts approaching 2.718281, blah, blah, blah. This number is the number e. It's kind of like this number, 3.14, is the number pi. The letter E represents the number 2.718. That represents something that is compounded continuously. So the number of times that we compounded just keeps getting bigger and bigger and bigger. This number, like this number, has a name. It's called the natural base. So when we're talking about exponent problems, the natural base is really our parent function. We use it like we use pi. It stands for something. E stands for 2.718. It's an irrational number. That means it goes on forever, it never repeats and never terminates, kind of like pi does. This is another name for this. The guy who discovered it, his name was Euler, so we call it Euler's number. And you treat it like any other variable. So like let's say, well, I'll show you that in just a minute. And then if you put it in the calculator, it'll show us like e to the first power. So let me show you where that's at. E is right above, do you see the little ln number? If I push second ln, it's e. And if I put into the first power, I get 2.17. I believe it's also right over here above the division. And same thing. So if you type in a lowercase e, you get the same thing. All right, so what I mean by use it like any other variable, like if I had e squared times e to the 5th, I would say that's e to the 7th. I just know that what I really have here is 2.71828 to the 7th power. So this actually means something, as to where x doesn't always mean something. So let's just take a look at a few examples of graphing e. So I would do this one just like I would any other exponential. I'm going to have an input of x and an output of f of x. So probably the first number I would try is 0. And e to the 0 power is just like any other number to the 0 power. You get 1. So it graphs 0, 1. And then if I put 1 in for x, I would have e to the first power, which we just saw was 2.72-ish. So I go over 1 up 2.72-ish. Then I would try negative 1. So I'm actually going to punch that into my calculator. I'll type in second ln to get that to pull up. And then I'm going to put negative 1 there. And I get 0.367. So at negative 1, it's at 0.367. So it's going to look something like this. Just like in the other graphs, I'm having nothing added here, so that means that it has an asymptote at 0. So this is going to keep getting smaller and smaller, but it will never get smaller or touch the number 0. So the domain on this one is negative infinity to infinity. The range is parentheses 0 to infinity. The y-intercept is at 0, 1, and the asymptote is at y equals 0 because we're not adding anything. So let's zoom out just a tad here. So I'm going to erase this one and think about what would happen if it was e to the x add 3. Well, if you add 3, that would change the asymptote. It would start up here at 3, and I would have an asymptote right here. So the graph would look something like this, but it would be raised up 3 units. Now, I would probably, if I were you, type something like this into my calculator. And I know that the numbers I want to start with are numbers that make this an even. So I would try 0, because e to the 0 is 1, and 1 add 3 is 4. And then the rest are just going to give you decimals. So you could go to y equals on your calculator, and again, you can use the graphing calculator app that's on your Chromebook. I would type in e to the x power plus 3. And then I would look at the table. And you can get all of the decimals you need there. I want to do a few more graphing examples with you. Let's do negative 3 to the 1/2 x power minus 5. So just by looking at this one, if I graph it, I know that the asymptote is going to be negative 5 because this has been shifted down 5 units. And then from there, I'm just going to be strategic about how I make my tables of values. I always want to start with 0 for x because anything to the 0 power would produce this thing to be 1. So negative 3 times 1 is negative 3. Subtract 5 is negative 8. So this one's going to be down 0, negative 8. And so since this is negative, that means instead of a growth, well, I'm sorry, this one would be decay because it's a half, so it's going to look like this. But because this is negative, it's actually going to be reflected down like that. So I kind of get an idea of what it looks like. If you would like, you can use the calculator. Again, use the graphing calculator app on your Chromebook. If you need help finding it, email me. I can help you locate it. So I would just type in negative 3, parenthesis 1 divided by 2, parenthesis, to the x power minus 5. And it will help you make a table of values. And we know that this thing is a depression because of the 1/2, but it's been reflected so it looks something like this. So this one is going to have a domain of negative infinity to infinity. The range is going to start down here at negative infinity, but it's only going to go up to 5. There isn't going to be a, well, I guess there is a y-intercept. It's where the x value is 0. So it happens at 0, negative 8, and that's where I put 0 in for x. And then the asymptote is at y equals negative 5, because that's how it's been shifted. Let's do one more. Let's cross this one off, and let's do 5. Let's do 5 times 2 to the x plus 1 minus 1. All right, I know that the asymptote is going to be shifted down a unit. So I know I'm going to have an asymptote down here at negative 1. I'm going to try a table of values. I always want to try whatever makes this 0. So what would I put in for x that would make that 0? Yeah, negative 1. Because negative 1 plus 1 is 0, and 2 to the 0 power is 1. And 1 times 5 is 5, minus 1 is 4. So I know that when I put that in the calculator, I should see negative 1 and 4. The graph looks something like this. See how the asymptote is down here at negative 1. I can check out some points that I want to graph by looking at the table. I'm going to try 0, 9, and then I already had negative 1, 4, and then I might try like negative 2, 1.5. So then I plot those, negative 1, 4, 0, 9, and negative 2, 1.5. So that thing is stretched quite a bit because of this 5 right here, and it's a growth because of that 2. You're going to want to use a graphing calculator or Desmos to find your tables.